Hey guys, today we're going to be talking about heat energy transfer. So there's going to be three terms you're going to need to know by the end of the day. Oops, first one is conduction, convection, and then radiation. Right away, you might notice that conduction and convection kind of sound very similar. There's only two letters different between the two of them, so just be aware of that. And hopefully, as we explain the difference, you'll feel good about the difference between the three of those. Let's start with conduction. So, question like, how does the house get electricity, right? You got a house over here, you got a power line over here, and then you got this thing right here. This is a wire. So, this is actually what the inside of a power cable would look like. Notice here in the center, you got stuff that looks like it's made out of metal. And then around the outside here, you've got some rubber. So the metal is going to help electricity kind of flow from the power line over to the house. And then this rubber over here is going to help prevent electricity from leaving the power line and then just going out into the air around it. So we would call the metal here a conductor, which is a type of material that easily transfers energy. And then we would call the rubber here an insulator. And an insulator is something that does not easily transfer energy. So kind of interesting how a wire has both conductors and also insulators. So conduction, here's what it means. It's the energy transferred, and here's the key, from direct contact between particles. I would make sure to write this down. I would also note at the bottom here that this is specifically for solids. If you're working with a liquid or a gas, they absolutely transfer energy through direct contact of particles, but there's also something else that happens, and we would call that convection. So know that conduction is direct contact between particles. That's how the energy change happens, or the energy transfer happens, and it works specifically with solids. I would have this definition written down in your notes. Okay, so I'm going to move on. Great. So here's a picture of a heat source, and then these right here are examples of particles. So maybe we're showing a wire or just an object in general here. And what I want you to notice is what happens to the speed of particles as they move. Hopefully you'll notice here that this first particle is moving the fastest and this last particle is moving the slowest. You'll also notice that these particles seem to be bumping into each other. And as they bump into each other, they start to move. So here, remember, movement is the same thing as temperature. So we're kind of simulating that a really, really fast moving particle or a hot particle is bumping into these other particles, kind of heating them up. Now notice that over time they slow down. That's just because heat transfer is never 100%. So yeah, conduction, if I had to summarize it down into like two words, I would say it's particles collide. That would be the two words that I would use to describe conduction. So sometimes instead of remembering a whole definition, it's easier just to remember a couple of words. So if that's the case for you, I would write this down. Particles collide, conduction. Okay, two terms you're going to need to know about conduction are insulator versus conductor. I talked about them a little bit earlier. Here, I want to show you particles. On the top, we have a conductor, and on the bottom, we have an insulator. And what I want you to notice is notice the difference here. That's what a conductor looks like. And then this is what an insulator looks like. Notice how with the conductor, the last particle is moving a lot faster than the last particle of the insulator. So, with conductors, there is a pretty solid transfer of energy. We might say that 80% or 90% of energy transfers from the first particle to the last particle. With insulators, there's not a very good transfer of energy. We might say that 5% or 10% transfers from one particle to the other. It really depends on the material. So a conductor, we would say, is any material that easily transfers energy, and a conductor is a material that does not easily transfer energy. So notice the difference here. It's all about energy transfer and whether it's easy for a conductor or whether it's difficult for an insulator. I would have these two definitions of conductor and insulator written down in your notes. Moving on. Okay, here are some examples of a conductor, and here are some examples of an insulator. I would pretty much write down any example that you did not know. So for example, if you did not know that water was a conductor, I would write that down. You can summarize copper, steel, aluminum as all metals. Pretty much all metals are conductors. And then for nonmetals, or for insulators, it's pretty much all other nonmetals that are not water or silicon. This last one here that says vacuum, that's not the thing that you use to clean your carpets. Here's what it looks like. You might have like a metal over here, and you might have a metal on the other side. And then in the middle here, you would just have nothing. Nothing. So a vacuum is actually the absence of space or the absence of particles. So if you look at like your thermos, like a Yeti mug or something like that, it's made of metal, but it's a really, really good insulator. And that's just because it's not the metal that's insulating it. It's that in between the metal, it's got a vacuum, which they call vacuum seal technology, which is just, there's no particles in here, so nothing can hit the metal particles and hit the other metal particles in between. So there's no real transfer of energy. So if you have tea, for example, it stays really, really cold. Or really, really hot, sorry. If you have iced tea, it stays really, really cold. So yeah, there you go. Examples of insulators and conductors. Okay, next type of energy transfer we want to talk about is convection. Here's a picture of kind of what convection looks like. What you'll notice here is at the bottom we have our heat source, and then you'll notice that as particles get heated, they rise, but then once they get to the top here, they become cooler, right? Because they're further away from the heat source. And we know that as we heat up particles, hot particles rise, right? But then as they get to the top, they get further away from the heat source, they can cool, and we know that cool particles sink. So convection is a cycle that we see with anything that can move really easily, any sort of liquid or any sort of solid. We call a liquid or a solid, we call that a fluid, or sorry, a liquid or a gas. A liquid or a gas, those are examples of fluids. And when you heat a liquid or a gas, they can rise and then they sink and then they rise and then they sink. And that process is called convection. So the definition I have is heating fluids causing particles to rise. I would also add something about sinking as well in your definition. Okay, so it turns out that convection has 4 steps. You don't have to write these 4 steps down, but they are helpful. This is called the convection cycle. So the first part is that the particle rises as it gets heated. That's just because its density becomes lower. The second step here is that as it rises, it's going to move further away from the heat. So now you'll notice it's almost at the top here. Third step, of course, as it moves further away from the heat, it's going to then kind of cool down. So now it's dropping once again. And then the last step is, of course, now that it's cooling, a cool particle is going to sink. So with liquids and gases, when they get heated from one side, like a bottom, for example, they have this cyclical process of rising as they heat up and falling as they cool down. And that's called convection. Here's a little animation of the convection process. Oh, come on. Tell me that's not cool. Oh, I'm so good at this. Yeah, so there you go, convection cycle. Here's just a picture of hot air and cold air rising. Sorry if this is super weird and super disorienting. Just to kind of show you that hot air, again, moves faster and cold air moves slower. Hot air has bigger spaces in between and cold air has smaller spaces in between. Here's a convection oven. You'll notice that it's got an element at the top, and you'll notice that it's got a fan. That's to kind of keep the air moving so that you can get a well-mixed oven and that it heats stuff up pretty fast. And then these are the same steps that I was talking about earlier. The last type of energy transfer we have to talk about today is radiation. Radiation is energy transferred by electromagnetic radiation. Electromagnetic radiation is a fancy way of saying light, but there's a lot of different types of light. Maybe some of these you've heard of before. So go ahead and write that down. Okay, this is the ER or electromagnetic scale. So I know this is a lot of information, just kind of bear with me here. On the one hand, we have things like radio waves. That's actually radiation. That's actually a type of light. We also, you'll notice we have AM and FM waves. We've got microwaves, and fun fact, Wi-Fi and 5G, those are both examples of microwaves. Also, think of microwave as like, the thing that heats up your food. We have infrared rays. We have the visible spectrum. So this is light that you can see. So like the fact that this picture is gold, that's visible light, right? Then we also have UV light, that's from the sun. We've got X-rays, and we have these things called gamma rays, which is the thing that made the Hulk the Hulk. Also, it's like what comes from black holes and pulsars and supernovas. So yeah, kind of super high energy. IR is infrared, and that's actually one of the ways that we use light to heat stuff up. So if you've ever been to a restaurant before, they have these little like heating lamps. Those heating lamps are giving off infrared light. So it kind of looks red to us, but some of it you can't actually see because it's below the visible spectrum, which means we just can't see it. Our eyes can't pick it up. So anyways, that's just kind of a lot of information to say there are many types of light, and you can heat up stuff in many ways. So for example, you can excite particles with an X-ray, for example, or you can excite particles with a microwave. A lot of different ways you can do that. But you could also do it with visible light or UV light or infrared. Anyways, what's going to happen here, since light is not matter, light is going to, in the squiggly line, is going to contact these particles. And then what happens is, once that happens, the particles start to just kind of move on their own. And so it's interesting here, particles are not contacting each other here, but light waves just kind of, we call it excite or give energy to particles, and that makes them move. So of course, as they move, they have a higher temperature. As they have a higher temperature, they have more energy. So radiation, another form of heat transfer. I'm going to leave you guys with this. This is a picture of the 3 different types of energy transfer. So you'll notice here, as the handle gets hot, that's an example of conduction. The water being boiled is an example of convection. And just this heating coil glowing is an example of radiation. Hopefully this picture makes sense to you as you see the 3 different types of heat transfer. Hopefully you're feeling confident about that. I hope this lesson made sense, and I hope you guys have a great day. We'll see you later. Bye-bye.